Welding armor, considerations for the next generation of ground combat vehicles. This presentation was originally given to the South Florida sections in April of 2025 based on research I conducted over the previous year while working in the ground combat vehicle segment of defense. And this is a summary of public information with references listed at the end. All images, tables, and other figures are believed to be from the public domain, are either licensed for use, or are the property of Weld Fusion LLC. Please read the disclaimer and note that all the references pertain to the use of armor in ground combat vehicles, and this does not imply any other applications which may have different considerations and approaches. This presentation provides an overview of ground combat vehicle classifications, next generation vehicle requirements, modern armor materials, considerations for welding, common discontinuities, and best practices overall. For reference, this transition has been happening for decades as historical designs are being replaced over time. As the references indicate, these materials have been around for a while, but next generation vehicle requirements are now becoming mainstream. So the time is now for many. Armored ground combat vehicles include infantry fighting vehicles such as tanks, personnel carriers, and also military engineering and rescue vehicles. Over time, historical vehicles and historical designs have had to be adapted to evolving warfare tactics. And this has increased overall vehicle weight and reduced agility. This picture from 2005 shows two soldiers that were involved with upfitting vehicles in the field with armor during a combat situation. In my role, I was contacted as a request to provide some materials to these guys who were out there on the front line, and they saw that the changing tactics required some instant modifications in order to protect the troops that were over there. Combat vehicle programs are being developed to be smarter, safer, and more efficient and adaptable to various terrains. These vehicles must increase troop protection, be rapidly deployable, easily configurable, and off the shelf that employ future technologies such as drone technology and remote control technology, all while reducing weight and improving vehicle agility. So the challenge was to improve overall armor protection while reducing weight and improving response times. But how could that be done? Traditionally, when you added weight, you increased protection, and when you wanted more protection, you added more weight. Well, designers turned to metallurgy and highly engineered materials such as high-strength, low-alloy, quench, and tempered armor-grade aluminum, and even titanium. These alloys are strengthened by alloying and often with heat treatment to obtain specific properties. These new materials provide the same or improved protection with reduced overall weight, helping to achieve the goal. Previous approaches to armor plating used heavy abrasion-resistant grades such as AR-400, AR-500, and AR-600 that many people have heard of. While these grades were harder than conventional steel, they were not designed with impact properties or specific applications in mind. It was basically just add weight of the most protective material we think we can find. As such, much thicker sections had to be used, and thereby it added more weight and really reduced the agility of these vehicles. So new steels and new steel alloys had to be engineered for specific applications, but really only two of them, A12560 and A46100, are really weldable. Other grades such as 32-332 are used only as applique armor or bolt-on armor. MIL-A12560 is intended to be strong and ductile. It's called rolled homogeneous armor to prevent fragmentation from blasts. 46100 is intended to be stronger, harder, and less ductile to stop more higher velocity rounds. And 32-332 is more designed as an applique, like I say. And the information I found said it's to stop larger projectiles. Dive into some weldability concerns. We're going to talk about some potential discontinuities. Also, we're going to talk about alloy content and how alloy content is going to help us prepare welding procedures that are going to preserve the mechanical properties of the material. And some of those welding requirements, processes, and procedures, codes, and standards we'll kind of summarize as we go. Now, while armor may seem a little bit mystical and a little bit like unobtainium, we're talking about general steel categories here. So many of the same discontinuities are going to apply. So we're going to see a chance for undercut. We're going to see the chance for incomplete fusion, porosity, too small of a weld size, et cetera, et cetera, et cetera. At the same time, we're going to have some different concerns that are brought about by the metallurgy, including hydrogen cracking, because this is a highly alloyed, or these are highly alloyed materials. Their carbon content is really at the high end of low carbon or at the low end of medium carbon steel, so it's not all that great of a concern. But because of the alloying, the carbon equivalent is much higher than that, and they're going to behave like a high carbon steel. So we need to really worry about hydrogen cracking and managing the balance between strength and ductility after we're done welding, or we could actually screw up the heat treatment and soften the material, or we could cool it too fast, make it too brittle, and it's not going to fail in the manner that it was intended. As we dive into the metallurgy, as we mentioned, 12560 and 46100 are really at the low end of the medium carbon range. So in the case of 12560, it's 0.27% carbon, not all that high. 46100 high hard has 0.32% carbon. So by AWS standards, we're looking at a 200 to 400 degree Fahrenheit preheat, followed by slow cooling, and we should be able to manage that. However, when we look at the alloy content, the increased alloy content making these things high strength, low alloy, quench, and tempered type steels, you're going to see that they behave like a high carbon steel, because the carbon content or the carbon equivalent is actually about 0.90. So we're up really in that high carbon content. They're extremely crack sensitive if we don't follow certain rules and guidelines, right? And these things are delivered as a tempered martensite structure. And as you know, or all welding folks know, when they learn about steels and steel metallurgy, when we heat a material into the austenitizing range and we quench it down to room temperature really, really rapidly, we're trying to form martensite. And once you have enough carbon or alloying content, that rapid cooling tends to form the hard, brittle microstructure that's definitely got wear resistance, but it doesn't have a whole lot of ductility. So by retempering that, we can restore some of the ductility to the material while retaining the strength and the hardness of the martensite. So that's really the trick behind what we're trying to preserve with welding, is balancing the hardness and strength with that ductility so that we can ensure that it fails in the way that it was designed. So these materials are engineered to perform using metallurgy by alloying specific elements together, by heat treating and creating certain properties, and then by tempering to restore some ductility to that strength. And if you look at the pictures on this slide, it shows the exit area, right? The backside of what can happen if we embrittle the microstructure, which also creates a condition where hydrogen cracking could occur. So something that we're going to be paying attention to are the conditions that exist that are prone to hydrogen cracking, right? We have sufficient carbon or alloy content. These things are going to behave like a high carbon steel. We have a susceptible microstructure. I mean, these materials are provided in a tempered martensite, so we already are dealing with a susceptible microstructure. In many cases, we have joint restraint, right, where we're fixturing these things or holding them in position. And the need to control hydrogen and cooling rate exists. So if we cool these materials faster than the critical cooling rate, whatever that might be for the alloy, we could create a more brittle microstructure, especially in that heat affected zone, and that could be prone to cracking and or fragmentation in the event that it is tested, because these things are tested how? In real life conditions when it matters. So Hydrogen delayed, cold, or underbead cracking all mean the same thing. They indicate that hard, brittle microstructure, a loss of ductility, and while that is strong and hard, it is brittle and sensitive. And what we're trying to maintain here is a sense of ductility. So heat input is absolutely critical, right? Our goal is to maintain the balance of martensite without embrittlement and maintain the ductility without overheating or over-tempering, which would actually soften the material. So it's a balancing act. Here, the as-welded condition is key, right? These materials have been engineered for specific applications and predictable behavior upon impact. Welding practices need to preserve those mechanical properties, and that's why we need to use qualified welding procedures that have been tested and qualified personnel that have demonstrated they can exhibit the techniques and perform the techniques required to achieve the desired weld properties, right? So it goes hand in hand. It's not rocket science, but it is weld science. Poor welding can lead to softening or embrittlement, which won't provide the desired level of protection, which could place lives at risk. So this is mission critical stuff. Both 12560 and 46100 armor have good weldability by industry standards, and success is largely centered on following best practices. Right, so we want to clean the material prior to welding. Both have thick mill scale from production and processing, and this is a source of contamination, garbage, and trash that can be introduced into the weld area. Remove the mill scale and reduce the chance of garbage contaminating your welds. Mill scale increases the chance of porosity, and I've seen it undercut way more than clean material as it burns off around the weld, especially on a horizontal fillet application. Use qualified welding procedures. You can't predict how welding will affect the material properties without testing. So develop your procedures, do the testing, and stay in the ranges. It's the only way to ensure predictable outcomes. Preheat is important. It eliminates moisture as a source of hydrogen, prevents thermal shock from welding, it improves penetration, and it slows the rate of cooling. Controlling preheat and interpass temperature will ensure that cooling rates are within limits and that temps haven't softened the materials. So it's really critical to monitor your temperatures. As a result, heat input is extremely important, and we're not only referring to pre and post heating, but also to process heat input in terms of energy over a given distance, right? So kilojoules per inch of weld, and that takes into account not only amperage and voltage, but travel speed. So if we sit there at a lower current level and it takes longer to make the weld, we could be doing more damage than if we used higher currents and traveled faster. Right? So too little heat input, we risk fusion and cracking issues because we may not have dilution that we need, especially on aluminum alloys. And too much heat input, we can soften the material, reduce strength, and thereby reduce protection of the armor material. If you haven't welded these materials before, it's recommended that you seek training and get qualified. Only qualified personnel are allowed to weld armor according to all codes and standards. Let's take a look at this application. The material is 2-inch thick, 12-560 rolled homogeneous armor set up in a double V-groove joint. Note the incomplete fusion and cracks that were found upon sectioning and running some penetrant testing. Upon further inspection, it was noted that the welder was not qualified and the weld was not made to procedure. Preheat was done at room temperature. Interpass temperature was not monitored between passes or after breaks. The assembly was not reheated after cooling, and poor technique resulted in bead overlap and incomplete fusion between layers. So this is an indication of just going back to basics and following the process and procedure, making sure that our welders are qualified and know how to make an acceptable weld joint, and we can resolve these issues. During a process inspection, monitoring revealed the following situation. There was insufficient cleaning of the base material. Note the mill scale and visible machining marks. There was no indication that the mill scale was cleaned to an acceptable level around the joint, and no indication that the coolant and fluid that may have been used for machining was cleaned or removed from the weld face. Incomplete fusion occurred in several areas because of poor welding technique and maybe incorrect parameters, right? Incorrect parameters did definitely result in globular short-circuiting transfer that contributed to fusion issues and launched spatter all over the weld face. And I noted that spatter was not removed prior to being covered up. And when you have molten spatter landing on solidified material around the weld weld, it's an area of lack of fusion. And if you cover it up, you're going to bury that lack of fusion down inside the material. So good practices are required to get good joints. Visual testing and inspection with magnification revealed some more issues with these materials. Note the visible overlap in what seems to be a toe crack near the weld in the first image below, exactly where the penetrant test indicated there was some issues in the other inspected sample. Poor workmanship and insufficient weld overlap resulted in a void in the image on the right, and still there's visible mill scale in the picture. Sufficient cleaning of mill scale off the material is more of an issue than you might think. It's a source of trash and garbage that's not good for any weld. Hydrogen, oxides, and other impurities can contribute to cracking, undercut, and porosity. It's just garbage. Insufficient preheat increases the cooling rate and the potential for hydrogen cracking in the heat affected zone. And unmonitored interpass temperatures could soften the material if things are allowed to get too hot during welding, or if things cool too much or too fast, it could create ideal conditions for cracking. Unqualified personnel simply don't have the background or abilities to weld on armor materials. The ability to read, understand, and follow the welding procedure is key. The ability to adjust parameters for optimum results within the welding procedure range is an important skill, and the ability to use proper techniques and adapt as needed because conditions constantly change under the hood. So these are things that the operator needs the ability to do and needs the ability to maintain during welding. Now let's shift gears and talk about aluminum for armor applications. Yes, contrary to popular belief, there is such a thing as armor-grade aluminum. By definition, it's the use of various aluminum grades in armor application where it's intended to lighten the load and provide a certain level of necessary protection. Ground combat vehicles often employ 5000 series aluminum for armor applications. It's non-heat treatable. Although 2000, 6000, and 7000 alloys may also be used, with only the 5 and 6000 alloys being readily weldable using traditional fusion arc processes like gas metal arc welding or gas tungsten arc welding. 2 and 7000 series often require solid state welding processes such as friction or friction stir, so that we don't experience cracking that can happen because those alloys are highly prone to cracking. As a welding article, we'll focus on 5000 alloys that are not heat treatable, right? 5052, 5083, and 5086, as well as some of the heat treatable 6000 series alloys. And we'll talk about how the condition of the material and the grade of the alloy influences our welding considerations. So why use aluminum? Well, first of all, like many industries shifting to this material, the primary factor is high strength to weight ratio. Couple that with good corrosion resistance, and you've got a lightweight solution for defensive protection. Aluminum is relatively soft compared to materials, especially steel and titanium that are used in armor, but in the right application, it does the trick. Aluminum welding challenges, potential discontinuities include all the common issues we see with pretty much every material, right? Undercut, incomplete fusion, porosity, cracking, and weld size, right? Insufficient weld size. But the cause and conditions differ slightly from steel alloys, and you might also see some soot material on the welds. Heat treatable alloys undergo a significant loss of strength in the heat affected zone, and thus thermal management remains an issue, right? So we have to control our heat input so as not to completely reverse the effects of heat treat conditions. Compared to steel, the properties of aluminum present significant welding challenges that, if not overcome, can keep you from making a weld of any kind. First, let's talk corrosion and oxide. Steel forms iron oxide or rust, which we can see, and left unchecked, it'll completely consume the metal over time, reverting it to its natural oxide form, right? Like a dust in a rock. Aluminum, on the other hand, forms a protective oxide layer that's invisible. We can't see it. It forms to a maximum thickness over the surface area, and it won't completely consume the parent aluminum material, at least for a really long time. However, you can't see it, so it's difficult to tell how much oxide layer has formed and how thick it actually is. At the same time, that oxide layer melts at a higher temperature than the base metal. metal. Pure aluminum melts around 1100 degrees Fahrenheit, and oxides melt at about 3600 degrees Fahrenheit. So that's about 3 times higher. If you don't remove the oxide, it's hard to form a puddle and make a good weld. Oxides can be removed chemically with surface cleaners, mechanically with dedicated aluminum consumables, right? Flap discs, grinding discs, and things like that that are specifically designed for aluminum, and by using stainless steel wire brushes and wheels that won't cross-contaminate. You can also see some cleaning electrically using DC electrode positive and argon shielding gas, which etches the oxide layer around the weld area. This is perfect for gas metal arc welding that uses predominantly DC electrode positive for applications, right? Wire feed applications. But that would eat your tungsten if you're TIG welding with DC electrode positive. So instead, with TIG, we use AC or alternating current to get cleaning as the current switches back and forth between negative and positive. Like steel oxides and mill scale, aluminum oxides can introduce trash into the weld. Think of that oxide layer as a sponge that holds moisture, right? A source of hydrogen and oxygen that really isn't any good for your weld. Aluminum also has a high rate of thermal conductivity, so it's harder to form a weld pool and requires more current than steel because it's dissipating the heat from the arc at a faster rate. This fast rate of thermal conductivity means the puddle wants to solidify quickly, and that can trap porosity. So those are the things we're going to talk about as we move through general welding practices to get good results on aluminum. One of the most common discontinuities associated with aluminum welding is porosity, which is directly related to shielding gas and the presence of hydrogen. Unlike steel, where hydrogen leads to cracking, here with aluminum it causes porosity. During welding, hydrogen is absorbed into the molten aluminum puddle because it has very high solubility. But upon solidification, the hydrogen is rejected or kicked out of the weld pool because it's no longer soluble, and that off-gassing can form gas pockets that are down in the weld pool, and rapid solidification can trap those pores before they have a chance to escape. And again, we call that often in the industry as off-gassing, allowing the puddle time to off-gas. Porosity can literally come and go with the weather, right? High humidity, failure to normalize temperatures of the material with the ambient temperature where welding will occur, improper storage or cleaning can all contribute to the dreaded Swiss cheese weld that's filled with holes and porosity. Aluminum is an excellent conductor, and even slight temperature differences can lead to condensation on the material. Couple that with an ever-present oxide layer that absorbs moisture like a sponge, and you've got the potential for big-time porosity. So what's the best way to deal with aluminum? Let's follow these steps from manufacturers. Double and triple check your shielding gas flow rate and all connections to make sure you have enough gas flow, that you don't have any leaks, because any leak can vent gas, and also if the velocity of the fluid or gas going through it is of substantial velocity, it can actually suck in gas and atmosphere through that leak. So we want to make sure that we're not pulling in any atmosphere or moisture that could happen. At the same time, if we're talking about shielding gas, inspect your consumables. Make sure that you don't have a clogged nozzle or any clogged gas ports up in the head of your torch. Clean those things out, maintain them, and usually you can work through this if it's your primary issue. The next thing you want to do is eliminate any hydrogen sources, primarily moisture, humidity, and any hydrocarbons. It's commonly recommended to first degrease your aluminum and then proceed to oxide removal, or you risk smearing around those greases instead of actually removing them. Oxides can be removed with a chemical or mechanical means prior to welding, and they often employ, as we mentioned before, DC electrode positive or AC current for cathodic arc cleaning action or etching around the weld. You can preheat to eliminate moisture and slow the solidification rate of the aluminum. And this is one case where a little dab will do you. Preheats for aluminum need to exceed the dew point, right, in order to be the most effective at eliminating moisture as a source of hydrogen. And 250 degrees is really the maximum you ever need to go because it's well above the boiling point of water. So all that moisture should be removed from the material when it approaches that 250 degree mark. Preheats for aluminum should never exceed 300 degrees as a maximum because aluminum is a funny material. it actually melts at a low temperature, right? About less than 1/2 of where steel melts. So that means all heat treating and thermal conditioning after formation of the aluminum alloy is going to take place at a lower temperature. And one of the things that we see is a process called aging or artificial aging, where the aluminum is heated to a temperature between 3 or 350 degrees and about 500 or 600 degrees, and it's held there for several hours, right? Time at temperature. And this aging process at first increases the strength of the aluminum. It continues to go up, the surface hardness, that kind of thing improves. So we see enhanced mechanical abilities. However, over-aging the material is like over-tempering or annealing and softening the material. So we have to be careful not to preheat too much and get into that aging temperature, or we could be doing detrimental damage to the mechanical properties of the base metal. So for that recommendation, or for that reason, we recommend 250 degree preheat maximum. It gets rid of the moisture, it slows the solidification rate, and is not significant enough to change the mechanical properties of the base material. All right, you can also optimize parameters for a more fluid weld puddle that solidifies slower and allows more time for that off-gassing to occur. This assumes you've got good argon gas coverage and sufficient flow rate. But I first saw this working in industry with early TIG inverters like the Dynasty machine from Miller. Customers would change from a conventional square wave machine like a synchrowave, and all of a sudden they would start seeing porosity when making the same welds with a Dynasty. Swap the leads and consumables back to the synchrowave, porosity would go away. Well, it's got to be the machine, right? The problem doesn't follow the swapped items. It stays with the product. Well, kind of, sort of. You see, the synchrowave produced a low and slow arc at 60 hertz. And that allowed the puddle to expand due to lack of focus, right? And that means it takes more time, or took more time, for the puddle to form. And that extra time put more heat into the material and preheated that area around the weld, which slowed the cooling rate. It allowed for off-gassing to naturally occur based on the technique the operator was employing. Okay, now we jump to the Dynasty, which has the ability to focus the arc right down using higher AC frequency output. It forms a puddle faster, right? A lot of people have commented on that. Wow, when I switched to an inverter, I hit the arc and boom, the puddle was formed right away. Well, what we saw was that didn't preheat the material around, so we got faster solidification rates if welding was to begin right away, like we were using visual indicators with our synchrowave machine, right? So solidification rate was much faster. Yeah, we could preheat. We could have added aluminum or helium to our shielding gas to slow the cooling rate. We could have lowered the 60 hertz arc down, or we could have lowered the frequency down to 60 hertz. I mean, we would have missed the whole point of using inverter technology. So instead, what we did is we told the operator to take a deep breath and allow that weld pool to slightly flatten out prior to adding any filler metal and progressing with their weld. And the result, that slight hesitation made all the difference. It slowed the cooling rate enough that the porosity was completely gone and we did not have to change the parameters at all. We just had to adjust the technique to deal with a new arc characteristic. Right? Okay. Materials also need to be stored correctly. And I've seen companies actually store aluminum in climate-controlled rooms to reduce the likelihood of porosity, right? Because going from a hot to a cold environment, cold to a hot environment, changes in humidity and dew point, we can all of a sudden see aluminum start to condensate and collect moisture on the surface when we didn't expect it. All right. So, at a minimum, when you're storing aluminum, you don't want to lay that aluminum flat. You want to store it on its edge, right? That way the edge is the only thing exposed to the surface if we're stacking multiple sheets together. All right, that's right. Stand it up on edge. Allow your aluminum to normalize to temperature. Don't store it outside ever, for one. It's not good practice. And don't put it in the shop 10 minutes before you plan to weld unless you don't mind a little bit of porosity in your welds. It's a good idea to let aluminum normalize to a temp over 24 hours before processing. Then follow best practices. There is no magic bullet to aluminum or welding, for example. Instead, it's understanding what's at play and how material properties work. Filler metal should be stored in its original packaging, wrapped and sealed to prevent moisture absorption and additional oxide formation. Keep your filler metal fresh and don't store more than you need at any one time. Aluminum is also quite crack sensitive, but unlike hydrogen under bead cracking in steels, aluminum exhibits hot cracking or hot short cracking, which is at the center line of the weld, and it occurs immediately upon or shortly after weld solidification. Some aluminum alloys can be welded without filler metal, but many require specific filler metal combinations to prevent this hot cracking. For example, 1100 aluminum is relatively pure and can be fusion welded or autogenously welded without filler metal. However, 6061 aluminum has both silicon and magnesium as primary alloying elements that require a filler metal with one or the other, but not both. Thus, to prevent cracking, we need a 4000 or 5000 series filler metal, but not 6000 because the combination of magnesium and silicon in the alloying elements would reduce strength and crackling would likely occur. Right? So manufacturers provide charts that recommend filler metal alloys for specific base metal combinations according to the intended service requirements. Those charts should be followed as a starting point for procedure development to make sure we have compatible alloys that are known to make acceptable welds. Many alloys rely on adequate weld dilution or the mixing of the base and filler metals in the weld pool in order to prevent cracking, even with recommended filler metals. This is another factor in filler metal recommendation for aluminum, and joints that promote high dilution are also recommended so the resulting admixture combination has the right ingredients to resist cracking. Welds that lack fusion or penetration are prone to cracking from inadequate dilution that limits the essential mixing of the base and filler metals. This often occurs at the start or end of a weld, especially with fillet welds where cracks can often be seen propagating from the root right up through the weld that I would refer to as a throat crack. As aluminum is a good conductor, it often requires more welding current to achieve desired penetration and dilution. And again, going back to our discussion about operator technique in dealing with porosity and new technology, the same thing is going to apply here. We need an operator that can recognize adequate penetration and ensure good dilution. If the operator can't see that happening or doesn't know what to look for, then we're going to start to have problems with throat cracking. Now let's talk about the fact that aluminum alloys lose strength when arc welded. In heat-treatable alloys like 2000, 6000, and 7000 series, the heat of arc welding causes something called precipitate growth, where the alloying elements collect at the grain boundaries and reduce strength in the heat affected zone. In the case of 6061 aluminum in the heat-treated condition, all of the alloying elements have been dissolved and evenly distributed through the aluminum. That's a process that heats the material and then quenches it after time to lock those precipitates in a position, right? So that they don't migrate to the grain boundaries upon slow cooling. So expect welds on these materials to see about a 50% reduction in strength post-weld and still meet code requirements. For example, the tensile strength of unwelded 6061 T6 is approximately 42 to 45,000 psi, and the AWS D1.2 structural welding code for aluminum publishes the as welded requirement of tensile strengths in order to meet code at 24,000 psi. That's a little less than a 50% reduction compared to the unwelded base metal. Why? Because even with proper filler metal selection, the heat of arc welding reverses heat treatment properties. Think of it as over-annealing the base metal. Then excessive heat input can further reduce strength and increase the heat of the width of the heat affected zone. Right? So heat is bad for these alloys. And I'm not talking about amperage because we need sufficient amperage to form a puddle, but we need to take steps to control our heat input. That's the combination of welding power over time. So hot and fast welding is the best. Now, non-heat treatable alloys like 3 and 5000 series don't see the same level of strength reduction after welding. The reduction is more minimal because these materials are not heat treatable, then instead they're cold worked or strain hardened to achieve their maximum properties. And this is simply not as drastic of a change as heat treating in heat treated and heat treatable alloys. In the case of arc welding, heat can reverse the strengthening effect of cold working. And again, this is minor compared to the loss of strength in the heat affected zone that can happen in heat treatable alloys like 6061. Now, because a loss of strength occurs in the base metal, filler metal selection really doesn't come into play here, right? That's more based on other factors. For example, 6061 can be successfully welded using either 4043 or 5356 filler metals. Both have higher tensile strength than 24,000 psi, and thus the base metal would fail long before the filler in a properly welded alloy. So in that case, filler metal really doesn't matter as much in terms of strength compared to what the base metal is going to end up at. In that case, we would look at other properties: crack sensitivity, corrosion resistance, heat treating after welding, those kinds, or anodizing after welding, right? Those are all factors that would consider more so what our filler metal should be in this case. If you've ever made a weld on aluminum and noticed a black powdery substance on the surface next to the weld, that's not soot. It's called smut. And that's an official term used to describe this purely cosmetic blemish that can occur on the surface of welded aluminum. That's right. It's not a weld discontinuity, not at all. Instead, it's actually vaporized magnesium condensating back on the aluminum surface due to the differences in melting and boiling point, right? It's most common in 5000 series alloys because those are the fillers that are high in magnesium. This is the most commonly seen with gas metal arc welding with 5000 series filler metals, and it's not very common in TIG welding, and most often is only observed if something goes wrong, like when you dip your tungsten in the weld pool, right? Make sure you have good shielding gas coverage, and you can also try moving your work clamp if you notice it collecting in one area and not another, because magnetic field will have an impact on where the material wants to condensate and the direction that it will follow, right? So as the magnetic field, the welding current has an effect. You can usually wipe it off after welding, but if you wait a while, it can get stubborn and require some scrubbing or even a wire brush to remove it. But again, it's not a discontinuity. It's actually vaporized magnesium recondensating on the surface of the aluminum. So in summary, many of the aluminum alloys that we're talking about here have good weldability, especially 5 and 6000 series. 2 and 7000 series are more difficult to arc weld, so procedure development is going to be critical. And just note that many of those alloys in those groups have to be welded using non-arc welding processes, what they would call solid state welding. You need to clean your material prior to welding. Think about this. That oxide layer melts at 3 times the level of the base metal. So that means you're going to really have to struggle to get good penetration down to the root, especially in a fillet weld, because if you don't clean the material, that's going to resist melting and fusion down in that area and be a potential discontinuity. Right? You need to degrease and remove the oxide layer. Degreasing removes hydrogen, which can lead to porosity, as does removing the oxide layer to get rid of moisture in the surface and make it so that aluminum melts at a lower base metal temperature, right? So that you can get good fusion and get moving quicker without putting in too much heat. Don't forget when you're welding aluminum to follow codes and standards, develop your welding procedures, qualify your personnel, and make sure that you're following the prescribed recipe that's been known to give you good results. If we change anything along the way, especially an essential variable, we're going to not be able to predict the outcome of the weld. And our guides here in ground combat code used to be what was called TACOM code or the TACOM code. Many of these programs now, as we're moving to new highly engineered materials, are falling underneath MIL specs, right? So MIL standard 3040 for steel and MIL standard 3057 for aluminum. Other codes that apply could include the AWS codes for structural applications, including D11 for steels thicker than 1/8 of an inch, D1.3 for materials less than 1/8 of an inch. We see the aluminum code being referenced, AWS D1.2, and in general, many codes reference AWS B2.1 for general qualification requirements and especially material classifications. So this is what we're going to see a lot of in the ground combat vehicle code area. Now, the old TACOM or TACOM code used to allow any trained or qualified individual to conduct visual inspection as a part of quality control. And moving to MIL standards, this has changed. MIL standards require any visual inspection as far as a qualified visual inspection to be done by an AWS certified welding inspector or an ASNT visual testing level 2 personnel, right? That has the qualifications to do the weld inspection. Other NDT requirements that you may encounter, we must have a documented procedure that outlines how testing will be done, whether that's visual testing, non-destructive or destructive testing, and again, must be done by a qualified personnel, and those things are all laid out in the code requirements. Surface inspections can be done by penetrant testing and mag particle, which again require a procedure and a qualified personnel that has the correct ASNT training. Internal inspections that can be used include ultrasonic or X-ray inspection, right, that are going to reveal what things look like below the surface that we can't see on the surface. That's normally used in this case called volumetric inspection for weld qualifications, but it can also be used for welder qualifications and for as welded part or product inspections prior to shipping to the customer. All depends on the requirements and the code specifications. Let's talk about best practices and inspection details. Inspection begins with a material review and a review of documentation. We need to look at the base metals, the filler metals, the joint designs, the shielding gases, and then leap into welding procedures and qualifications, right? So those welding procedures and qualifications are all tied back to base metal, filler metal, and shielding gas, and joint design, right, as essential variables. We should always be conducting our equipment inspections. Make sure that we, one, are operating in a safe environment, and two, that we have good accessories and good connections so that we're not generating unnecessary heat outside the welding arc or experiencing arc issues due to bad work connections, poor torch connections, maybe you're getting porosity, right? All those things need to be monitored. We also have our in-process inspections, right, where we need to make sure that we're following the procedure, that we're maintaining preheat and interpass temperature, that we are cooling at the right rate, that we are waiting the required time before conducting our visual inspections. And that the operator is indeed following at the welding current, okay? Post-weld inspections, again, we're going to make sure that we hold that armor for 48 hours. We're going to do visual inspection. That should begin with the operator. A trained operator should be trained to conduct preliminary visual inspection. And in my opinion, moving to quality should just verify that welding has met the requirement in order to satisfy customer documentation, right? At the end of the day, we're all in quality, and the first person in line is the person that did the job. So I like to say that our first level of inspection happens in the welding booth, and as we move forward, quality verifies that everything is working the way our system is designed. Okay, all inspections must be documented, right? In the case of armor welding, because a lot of times these things are going to entities and agencies that require a solid paper trail of documentation for traceability. And that's because lives are at stake. So these next generation materials used in ground combat vehicle applications do present some welding challenges, but following best practices can reduce the chance for discontinuities, just as making sure that you have trained and qualified welding personnel who are following those procedures, right? Following procedures and training your personnel increases your likelihood of success. And there are increased opportunities as these ground combat vehicle programs move to MIL standards, right? There's a need for more knowledgeable, skilled welders. There's a need for weld quality and inspection roles. And there are indeed need for qualified testing personnel above the visual inspection level. That includes penetrant testing, mag particle testing, ultrasonic testing, and radiographic inspection. So my tips for success: clean the base metal, use approved filler metals, follow an approved welding procedure, maintain preheat and interpass temperatures, and seek training and qualification if you need it. Okay, here's a list of the peer-reviewed references that I use to gather information to write this in a more comprehensive report. And I will post this for your review in a PDF of this entire presentation so that you can look into any of these references that you might want. Here's another page of additional references that include military specifications and standards, and some of the context and contextual sources for where we got some of the specs for modern armored vehicle requirements and the changing battlefield. Again, this is going to be available in the PDF version, so if you don't pause and write them all down here, you can go out, look at the PDF version, and get what you need. Some continued references that include metallurgical and welding foundations, filler metal specifications, and manufacturer data sheets.